Research rocket design. During your summer internship for an aerospace company, you are asked to design a small research rocket. The rocket is to be launched from rest from the Earth's surface and is to reach a maximum height of 960 meters above the Earth's surface. The rocket's engines give the rocket an upward acceleration of 16.0 meters per second square during the time T that they fire. After the engines shut off, the rocket is in free fall. Ignore the air resistance. What must be the value of T in order for the rocket to reach the required altitude? Okay, so the rocket has an initial velocity 0 starting from rest. Initial height is 0 meters. And it's to reach a maximum height of 960 meters. The acceleration will be 16.0 meters per second square for time t less than T, and it will be the free fall acceleration minus 9.8 meters per second square for t greater or equal to T. So we have gravitational acceleration g 9.8 meters per second square. Okay. Now, if I write dv dt, the rate of change of instantaneous velocity with time is equal to acceleration, I find that the velocity as a function of time is going to be equal to 16t for t less or equal to T. Then at time T, it's going to have a velocity v at T is equal to 16 T, and for t greater than T, it will have initial velocity 16 T minus 9.8 for time t minus T. So t greater or equal to T. So the velocity as a function of time. So the velocity at time t, T, is 16t minus 9.8 T minus t, so it is 16t. So I reach the same value of the velocity. Okay, so I have carefully written velocity as a function of time. Now for t less or equal to T, dy dt is the velocity, which is 16t. So the total displacement delta y as a function of time t from t equals 0 to t is 16 integral of 16t dt. This is 8t squared, 16 divided by 2t squared, so that the height that I reach at time T is 8 T square, since I initially start from ground. So delta y is 8 T square. For t greater or equal to T, dy dt is equal to 16 T minus 9.8 t minus T. So this is 16 T minus 9.8 t plus 9.8 T. So this is 25.8 T minus 9.8 t. So if I calculate the displacement delta y from time T to time t greater than T, this is integral from time T to time t, 25.8 T minus 9.8 t dt. So this will be 25.8 T times t minus 9.8 t squared over 2 this is to be evaluated between time t and capital T. So y at time t minus y at time capital T is 25.8 capital T times t minus 4.9 t squared. Then I will have minus 25.8 capital T squared. So let's do this carefully. So first I evaluated at time capital, here I have written the order incorrectly. This is from capital T to T. So first I evaluated at T, so it is 25.8 capital T times T minus 4.9 T squared. Then I evaluated at time T, so it is minus 25.8 capital T squared, and it's going to be plus 4.9 capital T squared. So I find that y at time t is y at capital time t, which is 8 capital T squared, plus 4.9 capital T squared, minus 25.8 capital T squared, minus 4.9 t squared. So if I calculate this, and I also have plus 25.8 capital T times t here. So if I calculate this, this is minus 4.9 t squared plus 25.8 capital T times t. And if I add these numbers, 8, 4.9 and minus 25.8, this gives me minus 12.9 capital T squared. So when I reach the maximum height at h equals h max, its velocity is to be 0. So at that point in time, velocity at time t prime, when I reach the maximum height, this is going to be 16t minus 9.8 t prime minus capital T is equal to 0. And this gives me, for t prime, 25.8 capital T divided by 9.8. So you can see that here this is 16 capital T minus 9.8 T prime plus 9.8 T equals 0. So I take 9.8 T prime to the right hand side, so I obtain this value, which is equal to 2.63 times capital T. Okay, so the position at that time, y at time t prime, is, because I have obtained this expression for y as a function of t, it's going to be minus 4.9 t prime squared, so it is 2.63 capital T squared, plus 25.8 capital T times T, 2.63 T prime, minus 12.9 capital T squared, and this is to be 960 meters. So this I have found is minus 33.9 capital T squared minus 12.9 capital T squared plus 67.9 capital T squared, and this adds up to 21.1 capital T squared. So therefore capital T has to be 960 divided by 21.1 square root, which is 6.75 seconds. Okay, so let's summarize what we did here. We are designing a rocket. The rocket is launched from rest from the Earth's surface, V00, Y00. is to reach a maximum height of 960 meters above the surface. The rocket's engines give the rocket an upward acceleration 16 meters per second square for time interval between 0 to capital T, and after that time it's free fall, so minus 9.8 meters per second square. So we look at velocity as a function of time, noting that the acceleration is time dependent here. It is 16t for t less or equal to capital T, and it is 16 capital T, its final velocity at time capital T, minus 9.8 t minus capital T for t greater or equal to capital T. Why it has to be like this? Because at time capital T, this has to be 0, and the velocities should match for these two parts. So I find that for t less or equal to capital T, dy dt is 16t. For t greater or equal to capital T, dy dt is 16t minus 9.8t minus capital T, parentheses. So I evaluate delta y between time capital T and t, first noting that I already reach a distance 8 capital T squared in the time interval between 0 to capital T by integrating v of t for t less or equal to capital T from 0 to t and evaluating this at time capital T. So it is 8t squared. And the integral from time capital T to time t, which is greater than capital T, gives me for delta y this expression, and I have to be careful for delta y is y at time t minus y at time capital T. So I obtain y as a function of t here. And at the maximum height, the velocity has to be 0. So at time t prime, the velocity is 0, which gives me t prime to be 2.63 capital T. By substituting this to y at time t prime, I evaluate y of t at t prime. It is 21.1 t squared, and that is the maximum height I will reach, so which has to be 960 meters. So taking the square root of 960 divided by 21.1, I find that I need 6.75 seconds for the initial acceleration of the rocket.